Hello and welcome everybody to this short presentation by my colleague Marie Sevnet and myself, Andreas Koch, on simulation-based support for the urban energy transition. In our paper, we try to combine the applied simulation work we do at the European Institute for Energy Research together with the more qualitative work we did in the past years on defining and scoping the needs of cities for urban energy planning.
This work is based on the widely shared observation. Climate change is now leading to a necessary energy transition of our society. In this context, the buildings are one of the main contributors. Consequently, the Paris Agreement emphasized the key role of local authorities, particularly cities, to scale up their efforts and support action to reduce emissions. Thereby, cities have to implement adaptation and mitigation measures at different scales, from the building to municipalities, even to metropole area. In order to be able to implement this measure, it's necessary to know the consumption of existing buildings in detail and to be able to simulate changes related to the energy transition. However, the lack of the data, especially technical data on the building stock, make it difficult to apply energy model. The problematic presented here aim to propose an energy simulation model for buildings adapted to the needs and constraints of energy planning. To fulfill energy transition, different stakeholders are involved from the building to the city. While the macro level provides objectives, regulation, and subsidies for the transition, communities must implement these objectives, and developers and owners must comply with the new standards in force. As the table shows, in the urban energy planning approach, climate and energy targets have to be identified at a city scale, to then be applied on energy concepts at district level, which eventually become the framework from the building concepts for implementation projects. In the following, planning support at both district and city scale will be regarded considering a quantitative planning support method. Urban energy planning at district level involves multiple actors, such as planners, architects, developers, local representatives, businesses, and sometimes local citizens. Such situations often result in the weak problem, with multiple objectives, value, problem tactics, complexity, and uncertainty. To avoid conflicts and misunderstanding, a data-driven approach based on a limited amount of input data helps to build a comprehensive and common vision on modeling.
When selecting the modeling approach, we gave preference to a simple yet robust model that relies on little or readily available input data, such as the mean outdoor temperature and the annual heating needs. In its simplest form, you can think of an energy signature as a regression depicted on the lower left side. So with lower temperatures, you would have higher energy needs, whereas there's a change point in this model that reflects the fact that there's no energy need in summertime, so flat parallel to the curve that is actually representing domestic hot water for residential uses, for example. In the application, we found the nonlinear model developed by Helwig. This is a signature function on the right-hand side, more useful as we see a declining increase at very cold temperatures in wintertime, and also a more smooth transition in the transition periods as it reflects aggregated demands, so there's not a sharp angle in there. For the application case, we compared the simulated to the measured daily energy needs for a group of 5 buildings. So we had the measured data on an hourly basis. We aggregated those to daily consumptions, and then we made the calculation based on the mean outdoor temperatures as well as the annual heating needs, which usually come from the billing for a residential sector, for example. And in the comparison, we did this for individual buildings, each of those depicted in line 1 to 5 at the table, as well as for the aggregated buildings at the lower line 6. And as you can see in the graphs, we get a mixed result for single buildings. You can see the spread, which basically we assume it's due to individual behavior, of course, which is not very well depicted in a statistic model. Yet if we aggregate even the small number of 5 buildings, we see that the fitness of the graph is improving greatly, which we see mostly in the root mean square error that is improving, as you can see in the table on the left-hand side. Whereas for the coefficient of determination and the correlation coefficient, we already got good results for the for the single buildings. There's more on how we compare this to the actual standards of ASHRAE and how we assume that the results would be good in the paper, and I'm also happy to answer questions on that either afterwards or by mail, of course. The results presented in this paper show actually the sensitivity to scale from data-driven models, which is not surprising due to their statistic nature. Yet they point at the applicability at even smaller scales. Here we looked at groups of buildings. We can well imagine a district or a neighborhood for simulating heating needs. Now, why we think this is important is that such simple regression models can be applied by non-experts and used also for continuous benchmarks over time. This is a fact that we saw in many projects. Once dedicated engineering teams left the project, we often saw that there's actually a need to follow up these projects and the performance of the project that is not necessarily fulfilled by City Hall. Now, this kind of tools we therefore think enables the community to better follow the performance and see the achievements, verify achievements, or in case it's needed, readjust the energy performance of the project to actually manage energy transition at city level. Thanks for your attention, and we hope to receive your questions after the session or by mail. Thanks a lot.